Well, weird. Yes, I know you're recording. Don't need to show me that. Yeah, I'll show the chat to the room as well, so that people can all see this. Yeah, couple of housekeeping things. Next Wednesday we're gonna be still here. I hope there will be more people showing up. There is 6 people in the room right now. I hope some more will turn up, but we will see. I strongly believe the lecture next Wednesday will be a very interesting one. David Leibowitz, he's a senior, I think, engineer or like, and technical person in a local company called Penten. So they do cybersecurity, many different kinds of cybersecurity. And what's more interesting for this class, I think, is David has, if you look him up online, he's done his PhD and earlier than other degrees in computer vision. His PhD is from the Oxford Computer Vision Group, one of the top groups in the world. But then he essentially navigated his career and moved away from computer vision. One reason I say that is computer vision is fun and exciting and challenging, but right now in the machine learning space, most students I met, they either send us an email or say, oh, they wanted to do computer vision or NLP or one of these when they study machine learning. So I think it's important to expose people to more machine learning than computer vision. Anyway, so that's a strong reason to attend next Wednesday. Next week and the week afterwards, we're going to break the graphical model tutorials into 2 to make them more manageable in 2 hours. And that will be all the tutorials. So there is tutorial material for the sampling lecture. We're just going to release it and not use a week to go through. The final exam has been announced. Okay, exciting. It's 3 hours. Your exam information sheet might say it's 30 minutes reading plus 2.5 hour writing. There is no distinction. It's just a 3-hour block on Wattle. We'll ask people to be self-invigilated and we'll send instructions sort of beforehand. I think these are, so every course have slightly different instructions, but I believe the self-recorded video option is actually being used. So for a lot of you, it wouldn't be new. So stay tuned. And also, I will also write it when we have instructions, but the previous year's exam are already on Piazza for those of you who care to look. There's one for 2021, there is one for 2019, but that was in-person exam. That was pre-COVID times. All right, so today we're gonna talk about graphical models, continue to talk about graphical models, in particular Markov random fields. We'll define what they are. We talk about conditional independence in them and compare them to directed graphs or base nets left and right. And then we talk a little bit about inference, where next Monday we're going to devote a whole lecture to inference. All right. Markov random fields are essentially undirected graphical models. The nodes are still variables. Edges are still some sort of dependency notions, except they are undirected. So they allow for different conditional independence statements than base nets, where in base net, the directed edge just translates to essentially conditional probabilities when you write out a join. In the base network, the definition of the block path was subtle for a HH node. So we already saw that, like for, we spent a fair amount of time to look at these structures. It's subtle because of 2 reasons. So the nodes above are conditionally independent if the head-head node is unblocked, right, unobserved. Furthermore, you have to also reason that any of its descendant nodes has to be unobserved as well. So that's kind of subtle and tricky. You wonder whether there's a better way to say these things. Right, MRF is partially addressed that. So we want and some other graphical semantics for probability distributions so that the conditional independencies sort of can be reasoned about in a simpler fashion. So yes, we gain something, we lose something. We're removing the direction from the edges, remove the asymmetry between parent and child nodes, which can be both good and bad. Right, so the subtlety, some of the subtleties associated with this head-head structure is lost, right? So I hope the people in the room can actually hear me. Yeah, okay, hi, Week09. Yeah. So let's formally define one notion of graph separation in undirected graph before we dive into what MRF really is. It's actually, so the definition of MRF is dependent on this definition. So in an undirected graph, G, having A, B, and C as disjoint subsets of nodes. For those of you remembering Monday's lecture, so at the end of the lecture, we talked about the way to reason about dependencies to look at 3 disjoint subsets. This is the same. And then we look at all the paths. If every path from A to B include at least one node from C, then C is said to separate A from B in G. Basically, right. So we look at all the nodes in A and all the nodes in B and look at all pairwise paths. If all the paths pass over nodes in C, then C separates A from B. That also implies that if there is a direct edge from any node in B, between any node in B to any nodes in, like between the nodes in A and those in B, then they're directly connected. Then nothing separates them, right? Okay. Let's just take a moment to compare this definition to this was directed graph, the directed graph version for base nets. Like, so it's Monday towards the end. We went through this. This is what we just saw on the last page, copied as is. So the things that are similar, right? So we have ABC as disjoint subsets in here, like ABC arbitrary non-intersecting set of nodes in directed and directed graph. On the left, it's rather simple. It just says, right, so in order to find set C that separates A and B, we can also simply find right, all the nodes on the way between A and B, and then just circle them as set C. So in directed base networks, it's less simple. So we the part about considering or the path from A to B between A to any node in A to any node in B is also the same. But what is not the same is this notion of path blocking in base nets include explicitly mentions of these 3 kinds of patterns, all right? Whereas in the undirected case, we just check if they are in C. And then the notion of separation is similar, and the conclusion is similar. So so last week, right? So we said if A or D is D separated from B by C, then A is conditionally independent from B given C. We haven't get to that yet on this page because we haven't formally defined MRF and what it represents. So now let's do that. So in MRF, when A and B are separated, so in an undirected graph, and when set A and set B are separated by set C, it implies the conditional independence as well. So a Markov random field is a set of probability distributions over a set of variables such that there exists an undirected graph G with disjoint subsets of A, B, and C, in which whenever C separates A from B, the conditional independence holds for the joint distribution. This is a mouthful question from week09. Every node in the graph is some random variable. And for the set of random variables, all of the conditional independence relations that look like this, no matter what A, B, and C is, would be encoded in the graph in the way that we defined on the last page. Right. So unlike Bayes' network, where the definition is, right, you can write out the join by essentially writing out the conditionals along the edges. And that way we have a one-on-one mapping between the graph and the factoring of the distribution. In here, mouthful basically says, oh, for this undirected graph, the collection of nodes and their edges, for all the conditional independence relations, you can find some set A, B, and C in the graph such that this is true, which is rather counterintuitive. It can be counterintuitive in the first version, first site. It also says that we probably don't make MRFs the same way that we make Bayes nets. And in example applications such as, let's say, my medical diagnosis, and on Monday we talked about, say, diagnosing whether like a broken printer, that kind of situation, the arrow is still very intuitive to write. But there is a procedure where we'll talk about where we can convert between the two. Okay, so how do we factorize a distribution that's represented by an MRF? We already hinted on this when we say when no, like set A and B, any node in set A and set B have a direct edge between them, they are not separated by any other set C, right? So, so we examine two nodes Xi and Xj that are not connected directly by an edge, and then giving all the other nodes of the graph, based on the definition of undirected graph separation, Xi and Xj must be conditionally independent. Because all the paths between Xi and Xj must pass through some other node, right? So that's kind of trivial. What that means is we write so this is essentially all nodes except Xi and Xj. And on the left-hand side, it is to say that given all the other nodes, what's the join between Xi and Xj? Given that the definition of conditional independence, we have Xi conditional independent of Xj given X, the vector X except I and J, then 8.38 holds, right? So they must factor this way. So reasoning about this almost trivial example tells us the importance of considering sets of directly connected nodes. So nodes, when there is a set of nodes that are connected to each other, namely cliques, for those of you who have seen a graph, which I believe probably discrete math will cover it, and graph and so on, algorithms will cover it, right? So how can we know that, for example, a triangle is a clique. So for nodes, the three nodes in a triangle, they cannot be like separated by anything. So this prompts us to use cliques as the one unit for factoring the joint distribution in a Markov random field. There we go. Okay, so first let's define cliques a bit more precisely. A clique is a subset of nodes in a graph such that there exists an edge between all pair of nodes in the subset. Namely, a clique is a set of fully connected nodes. A maximal clique of a graph is a clique which is not a proper subset of any other clique. Right, so here's a green clique, here's a blue clique, and the blue clique is maximal, but the green clique is not, because this green clique is a proper set of this larger green clique. Right, that's just a refresher. So here's factorization using cliques. A probability distribution P of X, the joint, factorizes with respect to a given undirected graph G if it can be written as a product of factors or potential functions. Yeah, okay. They're called potential functions in this lecture, some of it. So, and plus a normalization constant. So basically, the inside of these potential functions is some function that's defined over the set of cliques. They're just non-negative. And the constant z basically just normalizes this for it to become a proper probability distribution, right? So if the x's, all the variables take discrete values, then we just sum over the product of cliques over all the possible values to make sure that P of X sum to 1. It's computed like this, as you can see that if we have n variables and each variable is discrete, therefore at least 2 different values, then this summing operation is exponential in the number of variables in the graph. Right. So computing the normalization factor z for the entire graph is usually hard. This crib is going to appear again and over again, like in a few different places, right? So basically in graphical models, and then in sampling, we also talk about, yeah, there's this magical z that we don't know about. And we kind of hinted about this last Wednesday when we said, well, there's Gaussian process classification, and we can do a Laplace approximation. So the good thing about Laplace approximation is that the normalization factor of the original distribution don't really matter. Right. So there's that. So we're going to revisit the factorization again. But for now, let's just state without proving the relation between conditional independence of factorization both ways. So similar to Bayes networks, factorization, a particular factorization implies a set of conditional independence relations and vice versa. Right. But there are a few details, right? So in a strictly positive probability distribution, meaning no configuration of the nodes X have probability 0, which is not necessarily easy to satisfy. So, right. So if like strictly positive PDF satisfies the conditional independence statements implied by the graph separation over a particular undirected graph, then it also factorizes according to the graph. Right. The other way around, if a distribution factorizes, then the distribution satisfies all of these conditional independence. So this pair of theorems is very similar in nature to the ones in Bayes networks, and we will talk about whether they are equivalent in a little bit. So as the theory implies, strictly positive potential functions are nice to work with. So therefore, let's just define the potential functions as the exponential of another function called the energy function, E of xc. So it's so the energy function are not, they don't pretend to be probability, whereas potential functions are sort of unnormalized probabilities or components of unnormalized probabilities. So this is called the Boltzmann distribution. It's a name. There are many different. In the joint distribution, then we can rewrite this product of potential functions as basically a sum of energy functions taken to the exponent. So we have known in like the mixture model chapter and elsewhere that sums are nice to deal with, right? And the same normalization factor is at the front. The intuition between these two is that the potential function expresses which configuration of the local variables are more likely, more preferred to others. So does the energy function, because they have a monotonic mapping. And it's called the energy function because of also connection to statistical physics. So week09b. Good question. We'll see an example in a few slides, I think. Hopefully that will help. Yeah. So from online, Fei Yang is asking, what is a clique? A clique is a set of fully connected nodes. It's a subset of nodes such that between all pairs of nodes in that subset, there is an edge. Right. I also shouldn't assume that everybody has heard about a clique, because there's lots of people without a CS background may not have seen a graph representation. So basically, two nodes that are connected are cliques. Three nodes that form a triangle are cliques, undirected graph. Four nodes, so for example, in this four-node example, it's missing an edge, right? So if I add this particular edge, then it will become a four-node clique, and the blue thing will no longer be a maximal clique. Yeah, a five-node clique is a star plus a pentagon. All right. Yeah, you can go from there. Right. So what this definition also implies, right? So XC. Right. So it's nodes in maximal clique, right? So in the example of the previous page, if I remove the last edge that I drew, okay, I can't. Okay, I can't do. Right. So if I remove this extra edge that I drew, then right. So the set of nodes that the potential function will be written over is essentially phi of, we'll have a potential function term of x1, x2, x3, and phi of, or psi of x2, x3, x4. But we would not have, say x1 and x2, because this is not maximal clique. Yeah, okay. So on Wednesday, we'll talk about factor graphs, where the set of nodes are no longer maximal cliques either. Let's just stick to maximal clique for now. it is, as you can see, that the nodes in different potential function terms do overlap. And when we try to do inference or infer the marginal and conditional distributions, these overlaps create problems or dependencies that we need to think hard about. We'll briefly touch upon that as well. I hope that helps. Okay, Shulam, you'll ask, could you explain a bit more about configuration? I'm not sure what configuration refers to. If you can speak up and clarify. Oops. Or maybe we can address this a bit later. Or if anybody else here knows what configuration is. Right. Yes. Okay. Let's explain that. Right. So let's say we have a three node clique, x1, x2, x3, and they take values. For those of you know binary like tables, 0, 0, 0, 0, 0, 1, yeah, all the way to say what's the last two, 1, 1, 0, 1, 1, 1, right? Like binary digits. And then we can have psi of x1, x2, x3. These are unnormalized. So, for example, we will say the all zero state is quite likely. Just say 0.6. I'll say the all one state is even more likely. Okay, so 1.2. And then, yeah, these are cliques. So, for example, let's say we generally prefer when there's two neighbors sharing, like sharing the same state, and we want to discourage when the nodes at either end of the edge have different neighbors. So if we just have that heuristic, the potentials for, let's say, this state and that state will be about the same. So we say whatever, 0.2 and 0.2. So these are configurations. Basically, they mean the set of values that this set of nodes can take. And these can be, right, example, potential function. Yep.
Is there any reason that potential
function? So potential functions, they are not joint probabilities of these three nodes, let's say, because these same nodes appear elsewhere. If we require them to be normalized, then they are too restrictive. And we need to do the normalization work in that way, which we usually are not able to do efficiently. So I hope that answers it. Yep. Okay, here's the example you asked for. Right, it's in a book. So how about we use a simple Markov random field for image denoising? On this particular toy example that the authors came up with, I just drew this text box with some text in it, in the tablet of the early 2000s, and they basically then added some noise. This is a binary image, right? The pixels are either yellow or blue. 10% of the pixels were flipped randomly, IID, right? So the goal is to recover the original noise-free image as much as possible. So how do we use a Markov random field for that? Here we go. So for each pixel in the original noise-free image that we don't observe, remember we only observe this noisy image, which are these shaded nodes over here. We know that the shaded noisy pixels are determined from the underlying clean pixel with a IID sort of coin flip noise, right? So that becomes an undirected edge from the clean pixel to the corresponding noisy pixel. Furthermore, we connect each of the clean pixel to its four neighbors. We represent image as a matrix, so it's fairly straightforward to just connect a pixel to the pixel above below, and left and right. And what does the MRF do, right? So here we go. The energy function, remember the energy function is also just, I think it's the other way around. A lower energy function means that the corresponding configuration of nodes is more likely because there's a negative sign here. It's also because of physics. In physics, sort of lower energy is the more stable state, but okay. So let's take this apart, right? So the energy function between all the set of clean pixels X and all the set of corrupted noisy pixels Y is expressed as some constant H times the sum of X. I believe so. Okay, I think, right, so X here, Xi here is either 0 or 1. So the first term says 0 is more likely. Okay, yeah, that is true, given it's just some writing on the tablet, right? And then the second term says, right, the product of Xi and Xj, right, so it's sort of, right, so it wants the product of Xi and Xj to be large because there's a negative sign in front. And hopefully these coefficients are positive. Let's take a sneak peek. Yes, they are. Right. So this encodes the intuition that the neighboring pixels tend to be the same. And now the last term encodes the relationship between the noisy and the clean pixel, because 90% of the time they are still the same. Right, so I just do basically Xi times Yi multiplied by the factor eta, right? And then the whole potential function is simply 1 over Zx of minus this energy function. So how do you clean up the image now? What you do is the elements of Y, the noisy pixel is fixed. They are observed, right? And then we initialize X equals to Y. We know that's roughly correct for 90% of the pixels. And then we take, we look at each pixel one pixel at a time, and then evaluate the total energy for both possible states of +1 and -1, keeping all of the other variables fixed. So if flipping X leads to a lower energy state, then we flip it. If not, then we keep it. And we just then we do this basically a few times until no labels or no pixel value change anymore. And here's the result, right? It's not completely clean, like the original image, but it's significantly cleaner than the noisy image. So here is, oops, there's some technical difficulty about the meeting. Yeah, sorry about that. If someone online can send a link to the meeting, so I'm not sure if that's possible. So, well, that's being sorted. Let me ask people online and in the room a question. So why is this denoised image not completely clean? What could have been wrong? Yeah, you could do this sort of greedy flip at the time, but in here it's actually, the book says it's obtained by Graphical, which finds the global minimum, which we won't cover, but so it is not related to the particular choice of stopping criteria. On the other hand, it's because 10% of the pixels are flipped, there still could be neighboring pixels that were like flipped together. And in that case, it's harder to correct than just having isolated flips. And you can also have pixels that are flipped near the boundary of the drawing, where you weren't sure whether this part is really background or foreground. So the parameters for this MRF is beta is 1, eta is 2.1, and the preference for background is actually doesn't matter, it's set to 0. So going back to the energy function term, right, so this is 1, this one is 2.1, so means that there is a stronger preference for the pixel to agree with its noisy version. That's also another source of the image not being completely clean, right? Because there is the second term discourages, or the third term discourages flipping, right? So flipping is only encouraged when there is, for example, if this is a 1 to 2 term, then flipping one pixel value has to sort of agree with 2 more neighboring pixels in order to offset the effect of this last term. Right. I was wrong. So x is actually represented as -1,1. Another thing that we should notice is that in this whole process, we do not need to touch z. We just work on the energy function and then find its minimum. Done. We don't need to know what the normalizing factor is, because computing it can be a nightmarish computation, right? Because each of these pixels are binary, and I have thousands, or if not tens of thousands of pixels. So avoiding a hard problem is good. Now let's talk about directed versus undirected graphs. So we've seen both so far. There is one type of graph where the directed and undirected are kind of the same. That is chain graphs. So let's look at chain graphs in this example before moving on to the more general case of connecting these two types. Right, so figure 8.32 has a directed chain graph and an undirected chain graph. The claim here is that the factorization of the germ probability is the same. So for the directed chain graph, it's easy. We just write it out. Basically, every node depends on its parent node. It's conditional on its parent node, except the first node. That's all. And then for the undirected chain graph, what are the cliques here? Somebody who's not Vikram. What are the set of cliques in the undirected chain graph? Thank you. Right, so basically, yeah, the pairs of connected nodes. Right. So therefore, in fact, the notation here simply use the node label on the subscript, right? So psi of 1, 2 is a function of x1, x2, all the way to xn-1, comma xn. So with the only exception of the first term, which include the prior of x1, every other potential term is simply the later node condition on the earlier node. Another nice thing about this chain graph is, right, because they have the same factors, the partition function. So somehow the normalizing factor is called the partition function. Z equals to 1. So we don't need to compute it. We're done. Not every node is that nice, of course. So in general, how do we essentially try induce a similar kind of conditional independence between the base net and the undirected graphical models. So we do this. Because MRF's function, factorization, are over cliques, so we need to create those cliques. Because there is no cliques in the bag, right? So BaseNet is a directly acyclic graph, no cliques. So MRF, it's all about cliques. And the process for doing this is called normalization for, yeah, I think it's a historical name. There is no moral value implied whatsoever. It's positive or negative. We've already seen a few examples about this, right? Bias is not a negative term in machine learning. So just take this, yeah. Don't try and infer the semantics of this. So in a BaseNet, a node has parents, right? And we already know from last time that the common parents of the same node is this tricky head-head pattern that we don't like. We want to get rid of it. So the process simply connects the parents. Well, x1 and x2 are common parents of x4, so we can connect them. So is x2 and x3, and then we connect x1 and x3. Because conditioning on x4 in base network will actually induce dependency between x1 and x2 in this case, right? So this process is called marrying the parents. Having memorable phrases for the operation also helps. This is certainly a correct way of, let's say, encoding additional dependencies among the nodes. The statement also says that once we do this, we will not essentially have, we might have lost some conditional independence, but we would not have added any additional conditional. I hope that makes sense. This example here is, so once, for example, here are four nodes. Before that, before the converting into an undirected graph, we essentially have P of x1, the factors of Px2 and P of x3, and then P of x4 conditioned on these three things. After converting it to the undirected version, what we can do is, well, they're all part of a clique now. So this factorization is kind of gone. You might ask, what does this allow us to do? It allows us to do inference in the same way as Markov random fields, which are handy sometimes. So this process is kind of important. So here are two more examples. The question is A and B independent given D and F? So these are the, so we do this, right, moralize, connect A and B, disorient, remove all the arrows, and then delete the givens. A and B are still connected, therefore they're not mutually independent. Yeah, if we draw the base net, right, in the second example, A and B are unconnected. We draw the base net, which is isolated and moralized, disorient, and delete givens. They're still separated. So this is a way of reasoning about conditional independence, right? Which makes it easier to reason than trying to keep track of the three different kind of patterns that we talked about last time. Of course, whether it's easier is up to you. If you prefer to keep track of the three kind of patterns, that's also fine. So here are 3 more definitions, right? So a graph is a dependency map of a distribution if every conditional independence statement satisfied by the distribution is reflected in the graph. So a graph is an IMAP of a distribution if the converse holds, if every conditional independence implied by the graph is satisfied in the distribution. As you can see, we try to get a projection here. A graph is a perfect map if the D map and the I map are the right, if it's both. So why are we talking about this? It is because the for a set of random variables that has distribution P, right? So P of X is a vector in general. The directed graph representation and the undirected graph representation, they do not represent all the possible distributions, and they don't represent this. They also don't represent the same kind of dependence relationships. That's abstract. So here are 2 examples. Example, this head-head pattern, simple base net. It can be represented with a base net very easily, but you can't draw an undirected graph to represent. Similarly, this 4-node square thing as an undirected graph. It's impossible to draw a base network to represent the same kind of independence, right? So take the, right. So to see this, right, so what the undirected graph is best at is set A conditionally independent of C given C, right? B given C. But this head-head pattern actually has set A or node A conditionally independent of B given nothing or not given C. So that's different. And then for this square thing in the bottom, right? So A conditionally independent of B given C and D. And C conditionally independent of D given A and B. Yeah, that's not easy to turn into a directed version. So should A be the parent of C or the other way around? All right, so a few more quick about base nets and Markov random fields. What we said is the relationship between conditional independence and statements and the associated simplified algebraic structure is made in terms of the graph object. So basically, by reasoning on the graph, we can factorize the distribution and make conditional independent statements. Right, so and these statements, they are related to concepts of separation between nodes or subgraphs, variables in a graph. And the simplified algebra structure, basically factorization of P of X, is related to the local pieces of the graph, parent, child, or cliques. Right, so cliques are very local objects where there's a sort of furball of nodes that are connected to each other. Yeah. So these are the commonalities, which are handy. The differences, as we said on the last page, right, the set of probability distributions that can be represented by either are different from each other and different from the general set of joint distributions. So one thing to note is that the MRF has a normalization constant called the potential function Z. Another hidden secret of this Z term is that it couples all the factors. Every single factor is in there. It's nice if when we don't need to compute it, but when we do, it's kind of hard. And we have to think about like ways to break, like divide and conquer on this piece too. The local pieces of the Bayesian network, right? So this is an advantage of the Bayes net. Local pieces of Bayes net are probability distributions themselves. Vicom just asked, so, right, why don't we make the size distributions, because it's too hard. Right, in MRFs, they need to be non-negative functions. And they may not even lie within 0 and 1. And the theorem, like when they are strictly positive functions, it's nice. So it's easy to make strictly positive functions by adding epsilon to these potential functions. But it's not easy to normalize them. So then we move on to a little bit of inference for the remaining time. Okay, today we actually have a bit of time. Hopefully we don't need an hour and a half. Okay, it seems that the meeting has technical problems today. More than one. Help Zhao you get back in. So what are inference tasks in graphical models? I claim we did one with the image denoising. Basically, right, so we have P of X, which is the giant join of all the variables. We wanted to compute like marginal distributions. Right, so they take the form of P of Xi or P of something like P of Xi, Xj, and it can be others, and conditionals, right? Meaning P of Xi given Xj1, Xj2, and so on. You can say observing, so in yesterday's example, right, so the probability of grass being wet is related to rain and a sprinkler. Observing that the grass is wet and it's cloudy, what is the probability that the sprinkler is on? So you could do arbitrary conditionals. You don't have to condition, for example, child to its parent. So if I observe an arbitrary part of the graph, what can I say about the other part of the graph? Right, and these are called computing the posterior distributions of one or more subsets of other nodes. The general idea here is we want to exploit the graph structure because it factorizes. And there are many algorithms that are expressed like a local message propagation around the graph. So we focus on exact inference in this lecture and the next lecture. We decided not to cover approximate inference in this semester because I felt like you guys already had enough. And just doing inference is an essential step in learning. So the example on image denoising, for example, we just did is inference, right? So basically beta and C and H are known. Right. Learning would have been having to estimate beta, eta, and H from some label data, ideally. You could also do learning in unlabeled, but it's sort of harder. Like if I have many clean or kind of clean and noisy image pairs, I could estimate the relative strengths of these different terms. All right. And EM algorithm is mentioned here because the unobserved variables are unobserved to marginalize over them. And EM is not the only way to do it. Right? Okay, so let's start simple. Because thinking about arbitrary graph that can have a large number of nodes can be overwhelming. So let's start from just 2 nodes. What does inference mean, right? So if we just have 2 nodes, it's either x pointing to y, is either of them observed, or the other way around. In the first 2 cases, we essentially have, right, p of x, right, the factorization is p of x times py given x. That's join of p x and y. If we want the marginal of p of x, well, this is inference, so therefore the probability tables for these are known. Sometimes when one of them is continuous, it's not a table anymore, but they're all known. So we don't need to ask about marginalizing, just, yeah, computing p of x, that's known. We don't need to do that. So we care about computing p of y as the marginal. And what we do is we simply write out this term and sum over x. Then we're done. Sum over different values of x. Well, it can happen that, for example, x is the parent node, but it's unobserved, right? Like the clean pixel. We wanted to compute the posterior of x, basically. Given y, what is x? Then we essentially write out the same term, that's the join. The top 2 terms are known. Right, so what's the one in the bottom is computed above. Now that gives us the posterior. Simple base rule, nothing too fancy. What if the arrow is flipped? Then computing the posterior of x is then, right, in this case, p of y would have been known, and then p of x given y is also known. So we can just look it up. We talked about chain graph as the simplest sort of directed and undirected graphical model. So let's now try and do inference on them. So as we said, there are n-1 potential terms, 1 on each edge, or 1 representing each edge. And each variable appears in, most variables appear in two potential terms, with the n ones only appearing 1. So what we want to compute, let's say we want to compute the marginal distribution of p of xn. The naive algorithm is basically we sum over everything else, right? So these are nodes before or numbered lower than before xn. And then these are nodes after xn. Assuming each node takes up to k values, then this naive algorithm is exponential. So that's bad. But we can make use of one insight in that, well, we can eliminate the nodes. Some nodes are more important than others. So basically, the nodes that are close to xn influences the result. But the nodes that are far away can possibly be eliminated earlier, right? As an example, if we take the last potential term, psi of n-1 n, and we sum over that term over the values of x big N, we can see that x big N does not appear anywhere else on this factorization. So that's gone. Right? We can do the same for x1, actually. We can sum over x1 in the first potential term, then that's gone. Once these two are gone, our chain graphs essentially shrink. And we can do the same for like x2 and x-1 and so on. Oh, I think there is a typo. So these two labels should be flipped, I think. Right. So in that way, we can sort of divide and conquer until we get to the middle term. So summing over each of these potential terms is only k operations, and if we doing them sequentially, they don't need to multiply each other. So performing inference on graphical models, right, we're mainly after efficiency. All right, so here is the full expression expressed in intermediate symbols. The symbols are a bit scary, but we need them for next Monday when we talk about more generous graphs. So let's try and parse them here. We still have, right, this is basically the marginal of P of xn written out as is, right? So the difference here is we have separated the sum over each random variable inside, like in their order, right? So what? So we assume there are. So from the last page, we know that we can rearrange the sum so that it could eliminate, let's say, the last variable first. So here. So okay. So basically, it's the word, right? So like in here, the innermost sum removes x big N, and this one removes removing x1, right? And then one more, the sum after that, so this one further removes x2, and so on and so forth, until we get close to xn, the variable we care about. When we say divide and conquer, those of you with a CS background or have seen this dynamic programming paradigm or recursion, you will immediately recognize this pattern, right? So we define these intermediate terms called mu of alpha and beta, where our focus of attention is xn here, and this mu of alpha term, they're called, right, try to propagate messages from x1 towards n, and the mu of beta term try to essentially compute sums and propagate messages towards xn from the end, x big N. So it turns out that we can recursively evaluate them. Vikram. Yeah, good question, right? So let's parse this sum. Right. So the innermost sum is summing over, let's say, the outermost nodes, x1 and xn in here. We're doing this because, right, so without all, so if we try and read this expression without any of the summation signs, it's just a factorization of the whole joint distribution. We move the sum inside because there is only one term that depends on x1. As far as x1 is concerned, right, so on the last page, and this big expression, if I want to compute, let's say, p of x, color, p of all the other x except x1, what I need to do is, okay, 1 over z remains unchanged, and sum over x1, right, and then we have psi of 1, 2 term, psi of 2, 3 term, I'm omitting the stuff in the brackets, and then all the way psi of m minus 1 n term, right? We can basically do some pattern spotting and say, and identify that all of these like potential terms, x1 is not a variable, so they become constant, right? So the only term that matters is this one. So this is constant with respect to x1. So that's what we're doing, except like for all the variables, we do this. We essentially rearrange these terms. So in here, our focus is try to get the marginals of one of the middle nodes. Then what we do is we sort of rearrange these sums so that we can basically get rid of the nodes in the end first. So we do the same with x big N, because that's also only involved in one potential term. After we've done those, we can then go after x2, because now x2 is, so what happens is after x1 is sort of marginalized out or gone, this term, I use a slide maybe, this term. So the result of this sum and psi of 2, 3 will become a new term that involve x2 and x3. Summing over those will get rid of x2. Right, and the claim is that we can compute these mu, alpha, and beta factors recursively. Here we go, right? So let's say we call this term, right? Worked on this on the previous 2 pages a bit. We just sum over x1 for the first potential term, psi of 1, 2. That gives us mu of alpha as a function of x2. Still up. Display has gone to sleep. Right, so writing this term back into the previous page. So this inside here will become mu of alpha as a function of x2. Yeah, so it's not a constant. So we'll have a function of x2 and x3 multiplying the function of x2. We summarize. And now let's write this out for one more step, right? Then mu of alpha as function of x3 will be recursively essentially psi of 2 and 3, x2 and x3, mu alpha of x2 summed over x2. So that's how we marginalize our x2. So that's the next step in the recursion. More generally, we can just write mu of alpha as function of xn as basically multiplying the previous, call them alpha messages, with one additional potential term, and then marginalize out small x and minus 1. We do the same for nodes in the back. So these are recursion patterns, right? So mu of beta involving xn is computed on the basis of mu of beta for like x sub mn plus 1. As you can see, the forms are exactly the same. So we can do this. So how, right, we already said brute force. Doing this is k raised to the n minus 1. Now, we compute, like, if we want to compute one marginal using this, the complexity is n times k squared. Why is it n? Because there's roughly n sums here. Why is k squared? Because in each sum, we sum over k terms. It's squared because this marginal, this has k terms, meaning small xn have k separate values, and we need to do this computation for each separate value. All right. So if we were going to compute all the marginals, we just multiply by n, because for each variable, p of xn, it's order of nk squared, right? Now we multiply it by n. So if we store all the intermediate messages, it's also n squared k squared. So that's a lot. That sounds a lot better, right? It's a low order polynomial that we or we can actually expect our machines to run and finish. You may say, what about observed nodes? So the comment here is we clamped them. What does that mean? It means basically the observed nodes, the conditional probability. Let's say I want P of x5 given x3 is 2, something like that. Or I just want P of x5 given x3. So note that this one is a k by k table. That one is something like k length k vector, right? Right. So in order to calculate something like this, basically when we do this giant sum, we just remove the corresponding sum sign for that variable that's known, and then just use the value that we want that is known, essentially. Do the same for the recursion. Yeah. Right, so if we would like to compute the joint probabilities, what we do is, if the joint probability are on the two neighboring nodes, what we can do is we take these messages or factors, mu of alpha and mu of beta, and then insert the joint potential term. And then we're kind of done. So these factors, they are actually mathematical expressions, right? When the xn minus 1 and xn are not fixed, they are actually functions over the k possible values. We'll deal more with them next Monday. So if you find them a bit abstract, we'll see them again. Okay. So I believe this is the last content slide, right? So what we started by talking about general undirected graphs today. We'll say and we end with just chains. That's a bit like anticlimactic. Yes, it is, but hopefully by looking at chains, we get some intuition on how to reason about arbitrary large graphs. Another simple case is trees. So how are trees defined? For those of you who have a CS background, as a reminder, for those of you who don't, it's somewhat intuitive. So for undirected graph, a graph is a tree when there is one and only one path between any pair of nodes. Right, that graph A here is a tree, and there is no loops, no undirected loops. For directed graph, basically there is a single node called the root, which has no parent, and all the other nodes have exactly one parent. Right. You can have forests as well, where there is basically a collection of trees. But in that case, each tree is disconnected from other trees. We can do inference on them separately, and all of them are efficient. So what does this mean? It means when we try to turn the directed into undirected graph, or so-called moralization, they will not add links because there are no common parents of a node that are not yet connected, because a node can only have one parent in the directed case. Yeah, I am just gonna skim over and say inference for trees are nice. We can do this in the so-called sum product algorithm we will cover on Monday. That's all for today. Any questions? assume people are all happy. Go. But that directed polytree is not a forest. It's called a polytree because there are two roots. Yeah, but in this particular case, it also has this, that node in the middle also has two parents that are not yet. So in that case, I don't know exactly what the exact definition of a directed polytree is. I don't remember the book has defined that either, but let me just check on the fly. The claim here is that directed polytrees also have efficient inference. On the other hand, I don't see them too often. Right, it says directed polytree. There is still only one path between any two nodes. Right, it says, right, the corresponding moralized undirected graph will have loops. Yeah, of course it will. It doesn't necessarily mean that the clique will be small. So one bottleneck for inference efficiency is the size of the clique. You know, as we can imagine. We have a 2 clique find k squared. If we have 5 clique is k to the power 5.